Welcome back, guys. Remember these great minds. If you have not subscribed, please subscribe so that you can follow up on our videos. Okay, previously on our last video we were talking about hypotenuse testing, and we said in this video we'll be taking actual problems and be solving. Okay, so this is a question we have here. A sample of 14 tapeworm infected lambs was divided into two groups of 7. One group was treated with a drug and the other group was left untreated. After 6 months, the lambs were slaughtered and the following worm count were recorded. So you have the treated worm and the untreated worm, and these were the worm count that was recorded. Okay, so let's take note of the question. Now, the claim in this question we are trying to test is that test if there is the worm count was lowered in the slaughtered in the treated lambs. So we are testing if the worm count was lowered in the treated lamb. So this means that the claim is that the worm count was lowered in the treated lamb. Okay, remember we said, I'm going to wipe out here so it has space. Remember in our last video we said if you have a problem in which you have to conduct a hypotenuse test, first thing to do is to set your null hypotenuse. So we start solving solution. So the first thing we do is to set our null hypotenuse. Let's set our null hypotenuse. Remember we said it is denoted by H subscript O. See, now let's use S1 to represent the treated and use S2 to represent the untreated. So S1 represents the worm count of the treated, S2 represents the worm count of the untreated. Now remember we said we are using the mean, the average. So the average worm count of the treated, S1. Now we are dealing with, remember, two samples, two parameters, two different things, treated and untreated. So our hypotenuse, null hypotenuse, which is similar hypotenuse of no difference. So we see for the treated, it's same as the untreated. So we set our null hypotenuse that the worm count of the treated is the same as the worm count of the untreated. And the next thing we do is to set our alternate hypotenuse. And by our alternate hypotenuse is that, remember we said the alternate hypotenuse depends on the claim. And the claim here is that worm count was lowered in the treated. So worm count was lowered in the treated. That means the untreated worm count will be greater than the treated. We have this. Right? Which one did we use for the treated? Okay. So S1 represents, let S1 equal to treated and S2 equal to untreated. Okay, so S1 is treated, S2 is untreated. So we are saying null hypotenuse S2, which is the untreated, is higher than the S1. Yes, of our claim. Alright. So this is the first thing we do. We'll take so now we've taken our null hypotenuse and we've taken our alternate hypotenuse. So now we'll check again. The second thing we do is to check how many samples were we given. 2 samples were given, the treated and untreated. And remember we said when you have 2 samples given, the last time, in the last video, we gave the formula. So we use the formula. We are computing a test value, which we call the T calculated. Test value, which is the T calculated. So it is the mean of the first sample minus the mean of the second sample divided by the pooled square root of the pooled variance, times 1 over n 1 plus 1 over n 2. Okay, in our last class we gave out this formula. So we are to compute a test value using this formula, and after computing the test value, we test it, we compare it to a critical value, okay, to either reject or not reject unknown hypotenuse. Alright, so now let's find the mean. We can find the mean of the first treated, the first sample, and can find the mean of the untreated, the first sample. And to compute mean, I'm gonna wipe this away. To compute mean, now we know that mean S bar is given by the summation of, so this the mean of S bar 1, summation of the S1 all over, right? Now the summation of the S1 all over summation the n, the number of occurrence over the n. Now the summation of the S1 all over the n give us the mean of the first one, and so if you sum it, do that on your calculator, you obtain summation of S1. You can use calculator to do that. Input the S1s. Now you can use calculator to input the values of the S1 and just go to mode, the mode of the calculator. If you are using Casio, go to mode and go to start, which is option 3. Go to start, option 3, and you check the variables we are using. We have 2 samples, so you go to start, then go to option 2. Option 2. Then you can input all the values. You have S and Y column, so you input all the values that you guys have. So if you do this, you obtain the mean. If you input, and then after inputting, you can go back, clear everything, then go back to shift start, which is in 1. Then you find whatever you want, whether you want the sum, you want sum, this is sum. So over there you can find the sum of x and divide it. So when you do this, you obtain the mean. So if you do that with your calculator, you obtain the mean to be 26. Now we said okay, so you have 26. Where is it? 28.57. So if you do that, you obtain 28.57 as your mean for the treated. Remember we say S1 represents treated, and the mean of the untreated, so S bar 2, mean of the untreated, the same formula. So summation of S2, the values of the untreated, over the n. Remember what we said the n is in the last video? We said is the number of observation. So it will give you, if you also do that, you'll get, where is it? You get 40. You get 40.00. Yeah. So we can easily find this and this. So now the next thing we have to compute, I'm going to clean again. So let's take note of this. So the next thing we have to compute is our pooled variance. Our pooled variance. That's the next thing we have to compute. Now pooled variance is given by the formula the sum of squares of the sample 1, which is the treated, sum of square of sample 1, which is treated, plus sum of square of sample 2, which is untreated, divided by degree of freedom of sample 1 plus degree of freedom of sample 2. So I have sum of square of sample 1 plus sum of square of sample 2 divided by degree of freedom of sample 1 plus degree of freedom of sample 2. Now when we say degree of freedom is given by degree of freedom, which is same as df. df is just the observation minus 1. So 1 minus the observation, the number of observation, which is the n. In the question we had how many observations? 7. The sample was taking 7. 14 sample, it was divided into 7, so n minus 1 give you the degree of freedom. So this is same as degree of freedom. This is same as degree of freedom. So degree of freedom for the first treated and degree of freedom for the second treated. So let's also take note of that. Alright. So, and also, now we have proof variance to be this. So we can, and now the sum of square. To compute the sum of square, we also have a different formula for that. I hope you are taking note of all these formulas. As in subsequent questions, we'll just go straight forward. You have to take note of these formulas. Now, sum of square is given by summation. Where is it? Given by summation. So sum of square 1 has summation x 1 squared minus summation x 1 all squared divided by n n1. So let's take note of the formula. Say the sum of square is given by summation x, sum of all the s1, that's the treated, all squared. So summation of s squared summation minus summation of x into bracket all squared divided by the n. And summation of s squared, we can obtain that with our calculator. The same steps, you go to mode, then go to option 3, which is a start. Then when you get to your option 3, which is a start, guess we are doing with two variables. You go to option 2. Okay, input all the variables you are dealing with. That is the samples. The sample 1, the treated, you input it in the S column. The sample 2, the untreated, you can input it in the Y column. So when you are done with that, then you clear, go back to clear the whole thing, then go to shift start, then go and look for what you want. What we are looking for here is summation s squared. So you just go to option 3, which is sum. Then you have the s squared coming out. Remember, you imputed the first one, s1, you imputed in the s column. So you take the summation s squared, take it there. So if you can compute that with your calculator and find, so if you compute that, we'll get sum of square 1, ss1. If you should compute with our calculator, ss1. Remember, when you are solving, you are only allowed to use calculator to compute this, and use calculator to compute this. Then you just fix it in the formula. So if I should do that, I will obtain. So I'll clean this and get more space. So I have, where is it? I have 6906 minus 200 squared divided by 7. So the 6906 is my sum of s1 squared, summation s1 squared, minus 200 is my summation x, and 7 is the n. Alright, so when I do this, I'll get 1191.71. Right, so we'll take note of that. Get this. So now this is for ss1, the sum of square 1. Now we'll go and look for ss2, sum of square 2. We use the same formula for ss2, just that here comes 2, here becomes 2, and here becomes 2. The same formula, the same procedure. Can use your calculator to also do that. Just go and take sum of s squared to get it in your calculator. Remember, you imputed for s2 column, you imputed the y values, the s2 values in the y column. So in your calculator, you find summation y squared and summation y. So when we do that, we are going to obtain 12492 minus 280 all squared divided by 7. So if you take a good look at this, this here is our sum of s2 squared. This here is our sum of s2 squared, summation s2 squared. And this here is our summation s all squared. And this is our n. Alright? So when we work this, we'll be getting, where is it? We're getting 1, 2, 1292. So get 1292. Alright. So get 1292. So now we have our SS1, we have our SS2. So we'll go forward and substitute them into the equation. So now we can say our put variance, because remember S square represents variance and P represents pool. Our pool variance we can say is equal to have 119.1.7 plus 1292 divided by n minus 1, that's 7 minus 1 plus 7 minus 1. Okay, so these are pool variance. So you can compute this with a calculator. We'll compute this with a calculator. We're getting 206.98. We get 206.98. So that's our pool variance. Now we can. So now we have our pool variance. We can put it back into our formula to get our T, to get our test value. Sorry, put that test value. Sorry for the inconvenience. So now to get our test value, we have now we have our put variance, and remember our formula to get our test value. So we have the T calculated equal to, now we have the first mean. The mean of the first one we obtained was 28.57 minus 40.00 minus 40.00 divided by the root of we have root of 206.98. So 206.98 multiplying 1 over 7 plus 1 over 7. Remember our formula for T calculated, we just substituted everything. This represents the mean of the first one minus the mean of the second one divided by the square root of the pool variance, okay, plus multiplied by 1 over the n1, which is 7, plus 1 over n2. So when we compute this with our calculator, we compute this with our calculator, we obtain 1.49. So our T test value is 1.49. Obtain our test value to be 1.49. Now, in computing the test value or in solving hypothesis problems, we solve our problems computing the test values using a certain significance, and we use a certain so we use significance, we use the level of confidence. Compute at a certain level of confidence and a certain significance. Now when I say level of confidence and significance, what I mean is at what level of confidence, what percentage of confidence are you computing your work at? So this T calculated how much confident are you that this T calculated, if you compare with the T critical, whatever answer you'll be getting, you are true, it is true, a true answer. Okay, so mostly we'll be using 95%, because it's an agricultural something, use 95, but in most cases the question will give you, the question will give you the confidence you are using. So for this question we are using 95% confidence. We are using 95% confidence, so C equal to 95%. It's 95% confidence for this question. And now the significance Now let's take a formula here. Significance plus, so this is for confidence, and that's S represents significance. So confidence plus the level of confidence plus the significance level should give you 1. Or in percentage, you can say the level of confidence in percentage plus the level of significance in percentage should give you 100 if they are all in percentage. So if you are working at 95% confidence, then the level of significance will be, so significance will equal to 5%. Okay, so now after finding our t test value, after calculating the test value, you can go ahead to our t table. So now I have our test value to be 1.49. Remember, our test value to be 1.49. So now I can go to, so test value, let's put it somewhere here. T equal to 1.49. So now, in our last video, we said that we have a critical value that we compare the test value to, and if the test value should be greater than the critical value, we say we reject, we fail to accept the null hypothesis, we fail to accept the null hypothesis. And if the test value is less than the critical value, then we fail to reject the null hypothesis, we fail to reject the null hypothesis. Good. So now how do we get our critical value? Now critical value is computed from the t table. Compute it from the t table, statistical t table, which I have right here, and I'll show you how to compute that t table. Yes. And now the t critical is computed. Computing t critical, you have to know the significance level. You need the significance level, and you have to also know whether it is one tail or two tail, whether the problem is a one tail test or two tail test. And remember, in our last video we dealt with one tail and two tail test. And for a tail like this, where you are dealing with this greater than this, is a one tail test. So the test is one tail, so you have one tail. Okay, and then our significance, we say we are working at 95% confidence, and we say confidence plus significance is equal to 100. So our significance will be, so our significant level is equal to 5%. Okay, so one tail, significant level equal to 5, and then degree of freedom, we also need the degree of freedom. Now we are dealing with two samples, right? So we take the degree of freedom of sample 1 plus the degree of freedom of sample 2. That will give us the total degree of freedom. Then we can use the total degree of freedom to find the critical t, the critical test value. So remember the degree of freedom here, if the samples are 2, you add the degree of freedom for each of the samples. So we have, for the first sample, our degree of freedom was 7 minus 1. Remember we said the degree of freedom is n minus 1. Remember, let's put it here, df, degree of freedom is equal to n minus 1. N is a number of observation, so 7 minus 1 plus, so n1, the total degree of freedom we are taking it, plus the second, for the second sample, the degree of freedom for the second sample is also 7 minus 1. So put all together, this is, so degree of freedom is equal to 12. So our degree of freedom is 12. And it is one tail, degree of freedom 12, and 5% significance. So now we go to our t table. I don't know if you can see clearly. Let me bring it closer so you can see. Take our t table, bring it closer. See. So you have the t table. Now I have one tail here. You have two tail here. Now this column is column for degree of freedom. This column represents the degree of freedom column. And you have the significance at this column. So the one tail, these are the significance. This 0.05. 0.05 is same as 5%. Right? This 0.025 which is the same as 2.5%. Right? And you have 1%. Okay? So, and over here is for the two tail. If it's two tail test you are dealing with, use the second column, the degree significance of the second column. So we are dealing with one tail, and our significance is 5%. So one tail, 5%. So we are reading at this column, 5%. We are reading at this row. 5%, and our degree of freedom is what? Is 12. So come down, take 12, our degree of freedom 12. Then we'll trace it to where the column we are reading to. So 12, trace it to here. So our T critical value we can say from here is 1.782. 1.782. So we have the T critical. So T critical equal to 1.782. So now our critical value is 1.782 and our calculated T value is 1.49. So you have 1.49, 1.4. So now you compare. The next thing you do is to compare the calculated test value, compare it to the critical test value. Remember we said that when you compare, if the calculated is higher than the critical, then you can fail to reject the null hypothesis. But if the calculated is less than the critical, then you can fail to reject it, the null hypothesis. So looking at our critical T value is 1.72 and our calculated T value is 1.49. So comparing two of them, the critical is higher than the calculated, or you can say the calculated is lesser than the critical. So in that case, we are failing. In that case, we will fail to reject the null hypothesis. In other words, we will not reject the null hypothesis. So from the test value obtained, we do not reject the null hypothesis. So we do not reject the null hypothesis from the test value. So therefore, if we are not rejecting the null hypothesis, so that means the one count for the treated is not the same as the one count for the untreated. Now looking at our alternate hypothesis, so we can now say that indeed the one count in the untreated, in the treated was lower. We can say that because they are not the same, and since they are not the same, and we conducted the test, we were trying to prove the claim that the one count was lower. So from our test, we can then say indeed, yes, it was lower. So indeed, I say it was lower. So we fail to accept this, and we can accept that. All right. So that's it for this question. We'll take one more question. Then this for today. So let's take another question. All right. So we are looking at the daily weight gain. I'm reading the question. Taking the question. The daily weight gain of HIFES on 2 treatments of diet was as follows. It's as follows. The daily weight gain of HIFES on 2 treatments of diet is as follows. So you have treatment A, and have treatment B. And for treatment A, for day 1, you have 17.5. For treatment 2, you have 21.1. Okay, here you have 17.2, I have 19.5, I have 21.8, you have 21.6, I have 15.1, and we have 24.9, 20.0, so you have 20 here, you have 25.9, so let's put 9 there. Let's bring this 17.2, 19.5. So let's shift this here, 21.8, 21.8, 21.6, So you have this 15.1, 15.1, 24.9, 24.9, have this 20, have 25.9, 25.9, right? Okay, so we'll continue here. So you have 1, 2, 3, 4, 5. So you have 2 more, 3 more to go. You have treatment A. So we are continuing down here. So treatment A and treatment B. Okay, so we have 21.9. Here we have 30.2. We have 23.4. We have 24.9. And here we have 23.6. All right. So we say the daily weight gain of Haifa was taken after treating the two heifers, after treating the two group of heifers with a meal, with two different meal. So this is treatment 1. So with treatment A, meal A, we had these values. With treatment with meal B, we obtain these values. Okay, we obtain these values. Now the claim we are to compute, or we are to test is, we are to test if there is any difference between the weight gain of the heifers, between the weight gain of the heifers on the two meal, on the 2 meal treatment. Okay, so we are to test the claim, or we are to test if there is any difference between the weight gain of the heifers on the 2 meal treatment, right? So now remember, the first thing we do when we are given the question, when we have the question, the first thing we do is so I'm going to clean this so you have a space here. Remember, the first thing we do is to set our hypothesis. So set our null hypothesis, which we present with HO. So our null hypothesis given by. So now let's use mu to represent our null hypothesis. Let's use mu. So the mean, let's use mu to represent the treatment. So mu1, let's use to represent the treatment, the weight gain for treatment A. So this treatment A, this treatment B. So for treatment A, we use mu. So we have mu. And for treatment B, we use mu2. So mu1 for treatment A, mu2 for treatment B. Alright, so now hypothesis of mu difference. So we say that mu1 is equal to mu2. These are null hypothesis. Now we go to our alternate hypothesis, which is represented by H subscript A, and say that our alternate hypothesis. Now from the question said we are testing. Remember, we say alternate hypothesis, the claim is always found there. We are testing the claim if there is any weight gain. Okay, so that means the claim is there is weight gain. So that means the claim is there is difference. If there is any difference, there is any difference. So that's the claim. The claim is that there is difference, and we are trying to test that. So if there is difference, that means mu1 will not be equal to mu2. So these are alternate hypotheses. We are testing if there is difference. So alternate hypothesis. All right. So we take this. Now I can clean this so we can start solving. Okay. So now we set our hypothesis. Now remember from our last video, we said when we have a hypothesis like that, testing differences. you have an alternate hypothesis where you are just looking to test for differences. If there is any difference, that means it is a two-tailed. So from our alternate hypothesis, you can see that we'll be using two-tailed test for the work. The work is a two-tailed test, right? So we'll start as usual. How many samples were involved? 2 samples were involved. And because 2 samples were involved, our T calculated equal to, we shall have the mean of 1. So here we use mu. So mu1 minus mu2 divided by square root of the pool variance, times 1 over n1 plus 1 over n2. Right? Okay, so we clean this. Now remember, from our values in the sample, we have our mu1. I hope you wrote the question down so that you can follow up. We have our mu1, which is the mean of 1 to be equal to summation of the mu all over the number. Remember? So if you do that, you get the mean. If you do that, you get the mean to be so the mean of 1 to be 19.56. And if you find the mu2 using the same formula, so summation of mu2 divided by the number of mu2, that's summation of mu2 over the number of mu2, n2 number. So if you do that, you obtain 23.89. Get 23.89. Alright. So now we go on to find the pool variance. Record the way how we found the pool variance in the first question we saw. We find the pool variance, have a square p, set is equal to the sum of square 1 plus sum of square 2 divided by degree of freedom 1. Degree of freedom, it says n minus 1, don't forget. Degree of freedom 1 plus degree of freedom 2. Degree of freedom 2, so n1 minus 1 and n2 minus 1. Alright, and remember we said the sum of square 1, sum of square is given by the summation of mu, using mu, so summation of mu squared minus summation of mu all squared divided by n1. So when we do that, find the sum of square 1, we obtain 273. Remember, you can use calculator to find this and this. 273.51 minus 136.90 all over 7. All over 7. So the n1 for the first treatment is 7. Treatment A, the number of observations there is 7. So if you complete this, you obtain 55.14. So that's our SS1. So the same procedure, use the same procedure to compute the SS2. So we say SS1, we obtained 55.14. Now for the SS2, the same procedure. Remember, is sum of mu2 all squared minus summation mu 2 squared right, divided by N2. And if you do that, you obtain 4641.13 minus 191.90 all squared all over 8. So the number of observation for the treatment B is 8. Okay, so if you point this, you obtain 76.23. So if you do this, you obtain 76.23. Right? So you can now have the SS1, have the SS2, and so we can go ahead. SS1 and SS2, have them. We can go ahead to substitute them into this formula to find our pool variance. To have SP equal to SS1, we obtain 55.14. SS2, we obtain 76.23. Then 76.23 divided by degree of freedom 1. Now the observation for the first treatment A, we have 7 observations there, so 7 minus 1 plus degree of freedom 2. We have 8 minus 1. So when you compute this, you got compute that, you got 10.10. You got 10.10. Now 10.10 is our pool variance. So go back, remember our initial formula for T calculated, go and put 10.0 for the pool variance. So 10.0 for the pool variance, we have so our T calculated is equal to the mean had 19.56 minus 23.89 divided by the root of 10.10 by 1 over 7 plus 1 over 8. Right? So our T calculated, if we should compute this, after computing this, our T calculated, we obtain 2.64. So now 2.64 is our test value. The calculated test value that we obtain 2.64. Now remember, again, we go to critical. Now for this question also, the confidence, now problems that you'll be meeting, the confidence will be given. But if the confidence is not given and it is an agricultural problem, then you can use 95% confidence. So here we are having 95% confidence. 95% confidence we are working at. So remember if C is 95%, if C is 95%, which is our confidence, if it is 95%, then significance will be 5%. We said that C plus X equal to 100. Okay, so this is 95%, then this will be 5%. Right? So now let's go back to our alternate hypothesis. Now alternate hypothesis, from our alternate hypothesis you can see that this is a two-tailed test. So because it's a two-tailed test, so we are reading our T critical. So T critical, we read two-tailed, significance equal to 5%, which is same as 0.05. 5% is the same as 0.05. That's our significance. And our degree of freedom, DF. Remember we say we find the total degree of freedom. Degree of freedom for the first sample is treatment A plus degree of freedom plus of treatment B. And say degree of freedom is n minus 1. So treatment A, we have 7 treatment there. So n minus 1 will be 6. So you have degree of freedom 6 plus treatment B, we had 8. Degree of freedom will be 7. So 6 plus 7. Right? So this is 13. So you have T critical, as usual how we read it. So we go to the T table. From the T table, you can see that the T critical from the T table given by, okay, from the T table, you can see that the T critical, we read it. Let's clean this. We read the T table. Again, for this one we are using two-tailed. For this one, so let's come closer so you see it clearer. We are using two-tailed. So remember, two-tailed. We have two-tailed over here. So we are reading at this column, this two-tailed. We are reading at this row. We have 5%. Two-tailed 5% is over here, 0.05. So we'll be reading here. We're reading this column here. We're reading this column here. And then our degree of freedom is 13. Degree of freedom 13. So degree of freedom 13, you trace it to the column you are reading. So 13, trace it. Okay, have 2.160. Then 2.160. So our T critical, so critical test value have 2.160. Remember our calculated T calculated, our calculated test value we got 2.64. So again, you compare the two. So now if you compare these two, you can see that the calculated 2.64 is higher than the critical, which is 2.16. So for this one, the calculated higher than critical, so we can fail to reject. So we do not reject the null hypothesis. Oh no, sorry. It's the T calculated is higher than T critical, so we reject the null hypothesis. Remember we said if the T calculated is higher, is greater than the T critical, the critical T value, we reject the null hypothesis. So reject the null hypothesis. The null hypothesis will be rejected. Alright. So the null hypothesis is rejected. So if we reject the null hypothesis, so that means indeed there is difference. So we reject the null hypothesis. The null hypothesis was that there is no difference between the two treatments, but the alternate hypothesis is that there is difference between the two treatments. Okay? So take note of the correction, the mistake that we made, and the correction. If the T calculated is greater than the T critical, we reject the null hypothesis. We do not accept the null hypothesis. And if we do not accept the null hypothesis, that means the alternate hypothesis, we can accept it, it will be true. Alright. So thank you. We end our video here. The critical things you have to take note of is the T calculated and the T critical. If T calculated is high, then reject the null hypothesis. If it's lower than critical, accept or fail to reject the null hypothesis. Alright, thank you very much. We end the video here. Our next video we'll look at the ANOVA. Thank you. Make sure you don't fail to subscribe if this is your first time of learning with us, so that you can get our videos always. Thank you very much.